Alright, so I want to go over the notation that I have at this point. So these curly brackets indicate a generally unordered list of arguments to process over, and terms are separated within those by commas. Okay, so curly brackets, positive 4 comma negative 3, close curly brackets, equals, open curly brackets, negative 3 comma positive 4, close curly brackets. Classically, this is written as 4 minus 3 equals negative 3 plus 4. And also classically, subtraction is non-commutative, but when we do it this way, it is commutative. Okay, non-commutable terms are listed in order, left to right, and marked with a dot. So, that same thing, we start actually from 0. We have to define where we're starting from. So now it becomes open curly brackets 0, semicolon, because a dot and a comma together is a semicolon, plus 4 comma negative 3 close curly brackets is, etc. Okay, so this is the same as the above example, except that the reference frame is now explicitly defined as the non-commutable initial identity term 0. And the reason for this is that reference frame specification or respecification is the fundamental source of non-commutability. So now, what we have is a commutable list that is defined with a non-commutable reference frame defining term. And now within this, we can represent sequences of terms with an R for a repeating pattern, a U for a sequence whose unwritten terms are unknown, or a T for the termination of the sequence. This one's not so useful here, but for like a decimal expansion or something like that, the T can be quite useful. Okay, so this allows us to write all of the binary arithmetic operations, quote unquote, as commutative batch functions, which means we don't need to think about binary arithmetic operations anymore. Okay, so we can start with level 1, existentiation. There's 3 tiers to this, A, B, and C. We can define 0. This is non-existence. 0 has no dimension, but every dimension has 0. We can define 1, measurable existence, the dimensional unit. This is generally where you get things like natural numbers and those concepts from. And the infinitesimal existence. So these are not measurable distances. They are not Archimedean values, but they are continuous. They are atomic, right next to each other. There is no space between them. So those distances you can't measure. Those distances between them you can't measure. This is why these are not measurable, but they do exist. Okay, crementation. So this includes incrementation and decrementation. So the root part of that is crement. Alright, so here, this is the expression for incrementation. So this produces positive one-dimensional vectors. This is the notation for decrementation. This produces negative one-dimensional vectors, right? So this whole thing completely defines what negative k is. Right, so it seems a little like overkill at this point, but this is a much more thorough a much more thorough definition of this than you're getting from the successor function, because k doesn't have to be a whole number. Right? This is a dimensional unit, 1, but we're repeating it k times. K can be anything. K can be any way that we can find a magnitude, right? So this can include infinitesimals, this can include fractional distances, right? That k lends a lot of power to this, right? So k, positive k, negative k, these results are actually they include more values than the reals do, because the reals are not able to describe infinitesimals. So this is actually, like, it looks a little clunky compared to this, But the way that this is defined right here is massively more powerful than conventional mathematics even allows you to talk about. So, yeah, I don't care that it's moderately clunky. Level 3, summation. So now you can get addition and subtraction just from this, right? So we start with 0, and that is our initial reference frame defining term, and then we have these other guys, and these are one-dimensional vectors. Actually, they can be other vectors too. They can be more than one-dimensional. But here, so this u, I'm using this to indicate that instead of doing all this shit with like this ellipsis here, and we have to like write it all out, and it takes all kinds of space, you just put a fucking u right there, because I'm not entirely sure what's going on between those. There's just stuff happening, so it's a u. It's not the c term repeated over and over and over. There's more stuff in there. All right. Now there's a note here. 0 is not a vector, as it has no dimension. So including it in a summation anywhere other than the non-commutable identity term is meaningless. Any of the commutable terms can be 0, but if they are, we can just ignore them. 4. Plication. Hang on. I just realized something. Nope, that's not going to work. Okay. Alright. Plication. So this defines multiplication, this defines division. These two things right here, these are just prefixes indicating the multiplication prefix indicates that we're working with a magnitude, the division prefix indicates we're working with a dimension, right? So that gives us everything. Alright, any fraction, like k on a, is thus a vector by definition, since it has both a magnitude k, the thing that we're multiplying by, and a dimension, a. Okay. The nature of k determines how the evaluation works if a equals 0. A can be 0. It's simply not necessarily well behaved in a way that the people who think subtraction is inherently a non-commutative binary operation would understand, but caring about this is like asking a toddler to be an architect. Right? Do you really care what a toddler thinks about a building? In the same way, do you really care what somebody who thinks that subtraction is a binary non-commutative operation thinks about this? We've already gone well beyond what they can handle. So I don't care what someone like that thinks of this. I just don't. And there's no reason that I should. Okay? 5. Exponentiation. Notice here, this is level 4. Okay? We're getting up to tetration. Tetra means 4. So, Reuben Goodstein. Goodstein? I think he was British, so probably Goodstein. He clearly can't count. This is the 6th level, and he named it the 4th level. Anyway, exponentiation. So here, we can define exponentiation completely with these two things. It's just iterated multiplication. Okay? It's all right there. So if k is 0 in either case here, only the identity term expresses evaluating to 1. So it doesn't matter which way you're viewing it. We get a full definition of exponentiation, which defines positive exponents, negative exponents, fractional exponents, zero exponents, etc. All of them right there. And really, if we had a better notation than these, we could use that, but we don't. So there you go. Tetration. This completely defines classical tetration. Right there. Completely defined. This shitty notation. Okay. And this shitty name. Okay. We're stuck with those because toddlers. toddlers. That's why we're stuck with this bullshit. But basically what we're doing is we are taking our roots, our base A, and we are repeatedly raising it to powers. The first power we raise to is 1. So we end up with k exponentiations, with the first one being a to the first power. That's how it starts. And then it's a to that power, and then it's a to that power, and then a to that power, k times. Okay? The classical way this is described is it's k copies of a raised to each other or some bullshit, and the starting point is weird. It's over on the right hand side instead of the left, so you read it right to left or top to bottom instead of bottom to top like you normally do with everything else. And the number of exponentiations is not the number k that is indicated, and we have to separately define that if k is 0, then it evaluates to 1. So it just ends up being this giant pile of bullshit. Okay? And conventionally this operation is not correctly defined. But since its inventor thought that 4 equals 6, as I just mentioned, and he was mentored by Wittgenstein, whose doctoral advisor was Bertrand Russell, frankly, this is just par for the course. Like, none of this should be surprising to you. Like I said, these are fucking toddlers. They don't understand what the hell they're doing. They're just writing bullshit. They're like, oh, look at me, I got into college, yay, I can do mathies. Yeah, they're morons. Par for the course, okay? So note that with this notation, the classical operators simply indicate whether the terms are magnitudes, dimensions, or vectors. That's all they're doing, right? And thus, they're not actually operations at all. Also, every batch function is evaluated in exactly the same way, right? We have a single notation for everything here. From existentiation, from defining non-existence, existence, different kinds of existence, all the way up through numbers, integers, real numbers, multiplication, exponentiation, tetration. This would carry on to pentation, whatever, and we can finish defining them correctly so that it's properly commutative in here, and the only non-commutable object is the part that is defining your reference frame. Right? This is more elegant than even like lambda calculus, because there is no operator. It is literally just we're processing this list, this batch of items, this batch of terms. And all that we have is indications of the kind of thing that it is. Okay? Is it a positive? Is it a negative? Is it a magnitude? Is it a unit? Is it a full-on vector? Is this term repeated? And you could put an expression in here, so you can have you could have an expression in here that's repeated, right? So you can do infinite sums and infinite products, all with this one notation, and everything is now commutable. Everything is commutable. Except when properly indicated, where, right, we've got this little dot term, which is defining your reference frame. Because that's the only time, as far as I can tell so far, where we actually get non-commutability. Right, where you actually get a non-commutative operation is when we are switching between reference frames or changing the orientation of our current reference frame or something. Like we're going, like one dimension is becoming a different dimension. Something like that. Okay. And we can also, here you can see, when we're dividing, there's something in here that's non-trivial that is establishing our reference frame. And when we get division by 0 of that non-trivial thing, sometimes we get results, right? This is why L'Hopital's rule works. This is why when you're moving from a quadratic to a linear equation, you can divide by 0 if B and C are non-zero, right? You can do things now, and they make sense, and it's all tied together in one thing. But I'm sure everybody out there is going to be like, oh, you don't understand! Even though I just made this way the fuck more elegant, simpler, and everything is commutable now. There is no non-commutative binary subtraction operator. This is a commutative batch operation, a commutative batch function. I don't know how you want to talk about this, but all of these, it's the same exact commutative batch function for all of these operations. And they all have the same form all the way through. And I can explain all of it in one page. This is how shit actually works. Why we're following morons, I don't understand. Why we're following these people who clearly didn't know what the hell they were doing, I don't know. It doesn't make any sense to me. Why are we doing this? This is how it actually works.